In this particular recording, we're going to be looking at how to generate the dihedral groups with certain permutations. We do need to remember a few things from the previous recording, and so let me get that set up. First of all, we want our primary rotation to be the rotation that sends 1 there, 2 here, 3 here, 4 here, 5 here. This would be 6. And this would be where n goes. And the rotation has disjoint cycle form. It's an n cycle, and it's 1 goes to n minus 1, goes to n minus 2, and all the way down to 3 goes to 2, and that closes the cycle. The rotation is a 360 divided by n degree rotation in the counterclockwise direction. Now we also need, depending upon whether or not n is even or odd, we also want to be focusing in on one of the flips rather. And the situation where n is even, if we have a flip that fixes 1, then we are on a flip where the line of symmetry looks like this. And so 1 goes to 1, and 2 and n switch places, and 3 and n minus 1 switch places, and 4 and it would be n minus 2 switch places, and we finally wind up with k switching places with k plus 2. And this permutation, this flip, is going to be called S1 because it fixes S1, and for n even, the S1 flip is going to be 2 goes to n, 3 goes to n minus 1, 4 goes to n minus 2, and this keeps on going until you get down to k goes to k plus 2. And this is for n is even. The situation where n is odd is slightly different. Again, I want to focus in on fixing 1. So the line of symmetry would go like this, and the permutation would send 1 to 1, and it sends 2 to n and n to 2, and 3 to n minus 1, and n minus 1 to 3, and 4 gets sent over here to n minus 2, and n minus 2 gets sent to 4. But the ending part here is that k plus 1 and k plus 2 get switched. So when n is odd, the S1 permutation is going to look like 2 goes to n, 3 goes to n minus 1, 4 goes to, 4 goes to n minus 2, and the only thing is that the ending place turns out to be k plus 1 goes to k plus 2. So really the only difference between these two things is where they end. And if we look at a really quick kind of situation, you can see that. Just to kind of remind you, if we have something like a 6 cycle, then the S1 line would look like that, and S1 would be 2 goes to 6 and 3 goes to 5. But if I have something like a 7 cycle. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Let's see, we need to erase that and get a 7th vertex in there. And let's just darken up these vertices a little bit, make them a little bit bigger. Halfway around this time is this line. And so the S1 flip would be the permutation 2 goes to 7, 3 goes to 6, and 4 goes to 5. And so you basically start at 2 goes to whatever n minus 1 is, and 3 goes to the, you start with 2 goes to n, and 3 goes to n minus 1, and you just keep going until you run out. Now, the thing that we want to look at in this particular notebook is the following theorem from the textbook. And it says that any of our dihedral groups consists of all products of two elements R and S that satisfy these relations. And what this basically means is that they're saying that you can take one element named R and one element named S, and no matter how you string the R's and S's together, so let's do R cubed, S, R to the 5th, S, S, R to the minus 1, S, R to the 7th, that this guy here would be some element of dn. But now, using these particular things, we can simplify what's going on. Actually, these 3 rules, we can simplify what's going on, in particular in this particular element. And let's say that we are looking at, let's say that we are in low, I don't know, maybe D8. We would basically start by using the associative thing, and there's an S squared, and S squared is equal to the identity. That 1 can be written as E. And so we would be looking at R to the 7th times S times R inverse. That drops out. That's an R to the 5th times an S times an R cubed. And let's see, we would have an R to the 7th times an S times an R to the 4th times an S times an R cubed. And if we keep going here, we can use this thing here to basically wind up, though this is a little bit tricky, this thing here will wind up becoming an R to the 7th times an R to the minus 4 times an R cubed. And that would simply be, it looks to me like an R to the 6th if I've done all my arithmetic right. But that's not really the whole point of what I'm wanting to look at, although we're going to see how that behaves in not too long. What I really want to focus in on in this particular video is the proof of this theorem. And it's done in steps, and the easiest part of it is the first part, where when the author says the possible motions of the regular ingon are either the reflections or rotations, we already know that. That was in the last video. And there are impossible rotations. And remember that our primary rotation, the R from the previous slide, was 1, 2, 3, 4, 5, 6, and this went to n. And what we want to notice, and this was in the last particular video is that if I have one of these other permutations, if I have one of these other rotations, that rotation that is written as k times 360 degrees divided by n, that basically represents k steps in the counterclockwise direction. In other words, k squared, in other words, 2 times this guy would send 1 2 steps away, 1, 2. So it would send it to n minus 1, and it would send 2, 1, 2, and it would send 3 to 1, and it would send 4 to 2, and it would send 6 to 3, and so forth. And it turns out, and it's very easy to see this, and we actually did this in the last video, that if r is equal to 1, goes to n minus 1, goes to n minus 2, goes to 3, goes to 2, and goes back, if we set r equal to that, then it's very easy to see that r to the k is indeed the permutation that represents k steps in the counterclockwise, let's say k steps in the counterclockwise direction. So we have all of the rotations clearly written as products of just r itself, and we don't have to worry anymore about that. Well, what about the rotations? Well, that's where this particular proof gets a little bit weird. And I want to kind of highlight this one step at a time. First of all, the author is talking about labeling rotations that leave the vertex k fixed. And I kind of want to do just a little bit of that. One thing that I want to notice is that S1 is just going to be our flip from the previous video, where 2 and n switched places and 3 and n minus 1 switched places, and eventually we get down to k plus 2 switches places with the vertex k, which is on the other side of k plus 1. So S1 would look like that one, so S1 looks like 2 goes to n, 3 goes to n minus 1, 4 goes to n minus 2. You keep going until you finally get to k, and k goes to k plus 2, because k plus 1 and 1 are both fixed by S1. If I get a different color, the S2 permutation would use that red line for its line of reflection, and so it would have 1 and 3 being paired up and 2 and 4 being paired up, and k plus 1 would be paired up with k plus 3, and so on. And so it's important to realize that when the author is talking about S1 is equal to Sn divided by 2 plus 1, that's the orange things over here. And when the author is talking about S2 is equal to this guy, that's the red line. And so on and so forth. Now, that obviously only takes care of half of the reflections, and the author does not mention that. And I'm not quite sure why, but it's kind of important to realize that the SK flips are only half of the flips when n is equal to an even number. The other flips are the flips that don't fix any the other flips are the flips that don't fix any of the vertices. I called the first one S2 hat in the previous video, and S2 hat had a line of reflection that looked like this. So S2 hat had 1 and 2 flipping, and 3 and n flipping, and 4 and n minus 1 flipping. And eventually you get down to k plus 1 and k plus 2 flip. So S1 hat is the permutation 1 goes to 2, 2 goes to n, 3 goes to n minus 1, and you keep going until you wind up getting k plus 1 goes to k plus 2. And there are n flips of each of these types. And we saw that last time as well. It's important to realize, well, the other one that's easy to see here would be, and let's get this into a different color. If I used that line for my line of reflection, then these two vertices would flip, and 2 would flip with 5, and 1 would, these two would flip, and n would flip with, rather 1 would flip with n minus 2. Now it turns out that we have to account for both of these kinds of flips when we are at the end of this proof. But the next thing that the author says, of course, is dealing with the odd ones. Well, if we have an odd number of vertices, then it turns out that all of our flips have one fixed vertex, and the line of symmetry goes to the opposite edge. And so S1 would be this line of symmetry, and in S1, 1 goes to 1, and 2 and n switch places, and 3 and n minus 1 switch places, and 4 and n minus 2 switch places, and then eventually we get down to k plus 2 and k plus 1 switch places. So when n is odd, the S1 permutation is going to look like 2 goes to n, 3 goes to n minus 1, 4 goes to n minus 2, and it keeps going until we get down to k plus 1 goes to k plus 2. And it's important to realize that the only difference between the S1 for the odd ends and the S1 for the even ends, let's go back to that page. Here's S1 for the even ends. The only difference is where they end. But they start out in the same basis, same way, and you just keep going until you run out of things. Again, the other permutations over here would work the same way. The other flips would work the same way. The flip from n would go to the edge that is right before this one. And so it's kind of hard to see, but we've seen this if I draw a nice pentagon. We can see it in that the flip lines are going to look like that flip line, this flip line, this flip line, this flip line and this flip line. And that would be the flip line for S1. This would be the flip line for S2. This would be the flip line for S3. This is the flip line for S4, and this is the flip line for S5. So when it is odd, it turns out that the SKs are all distinct. And so we pick up all in flips by just looking at the SKs. And the next statement in this particular proof is really easy. All of these things are flips, so of course the order of each of them is 2. You flip a flip, you do a flip and you do it a second time and you get back to where you started from. And then the next thing that the author says is we're going to let S be S1. And so we're simply going to let, regardless of the case, so regardless of whether n is even or odd, we're going to let S1 be the magic S that the theorem is wanting. And all we're doing is we're saying we've got a candidate for S. S1 is our candidate for the S promised in the theorem. And clearly, the order of S is 2, and the R is, as we've already looked at, it's going to be the R that we've already done. So now we're going to look at where the proof really starts to get peculiar. The author says, since any rigid motion T of the n-gon replaces the first vertex by the vertex K, the second vertex must be replaced by either K plus 1 or K minus 1. Well, we have to figure out exactly what the author means by that statement. It's easy to let that statement just roll over you like a wave without fully understanding it. And what we've got to do is we've got to realize that what the author is saying here is that the vertex that gets moved to the 1 spot is going to be the vertex called K. And one of two things happens. The vertex that gets moved to 2, the second vertex, the vertex that gets moved to 2, can either be K plus 1 or K minus 1. So our case 1 is going to look like this is K minus 1. Nope, I guess this is going to be K plus 1. And our second case is going to be K got sent to the first spot and K minus 1 got sent to the second spot. Now we have to actually figure out what goes on in each one of these cases. So we're going to look at them individually. In our first case, we have the 2 vertices there like that. Now we know that it's a rigid motion of the n-gon, and that forces this guy to be K minus 1, and this guy to be K minus 2, and this guy to be K minus 3, and so on. And this guy is going to be K plus 2, and this guy is going to be K plus 3. And what I want to notice is that the order of the k's going around on the inside circle, they are increasing in this direction. And they are also increasing in this direction. Now, I want to remember something from the last video. R since 2 to 1, r squared since 3 to 1, r to the 4th since, well, let's start with r cubed. R cubed since 4 to the 1, r to the 4th since 5 to 1. In general, r to the k minus 1 since k to 1. And I kind of want to look at why that works. So I'm going to have my n-gon here. But this time I'm going to focus in on whatever the k is. And this is the beginning of our cycle. And 1, 2, 3, 4. We keep going. And let's see, k minus 1 is there. K plus 1 is here. We keep going. And eventually we get to, that's in, this is in minus 1, this is in minus 2. Now this is the original labeling. Now when we do r to the k minus 1 on this particular n-gon, the labels get shifted in a counterclockwise direction by k steps. Now, what I want to realize is that k steps goes the same in both directions in the sense of counting. And if I go the wrong direction, this would be 1 step, 2 steps, 3 steps, all the way down to, well, let's see, 1 step, 2 steps, all the way down to, this is k minus 1 steps. So from here, let's give this in a nice bright color. From here to here is k steps in the wrong direction. So from here to here is k steps in the correct direction. So what that means is that k lands there. And of course, k plus 1 is going to land here. Let's get into a different color. Ooh, that's a bad color. Maybe what I need to do is, well, let's see. There's a color that I can see. And this one here is going to land at k minus 1. So what we can clearly see is that the labeling for, let's see, the labeling for r to the k minus 1 is going to look like, well, I'm going to do this on the inside. On the outside labels, the original labels looked like this. But once we do the shift, the new labels look like k, k plus 1, k plus 2, k minus 1, k minus 2, and that is exactly the picture that we have in case 1. So if we just go back up and look at case 1, this is indeed exactly this picture here. Let's in fact try and move that whole picture. So we will copy all of that. And actually we want to clone it. So let's clone it. And we're going to take that and we're going to continue pulling it down here. And if I compare the labels here the inside labels here to the inside labels here, we've got the same labels. So case 1 is just r to the k minus 1. Now, if we look very carefully, I want to remember that. Case 1 is r to the k minus 1. Our author has actually made a typo. In this green sentence, that is a typo. Yes, math books sometimes have typos. That should read that t is equal to r to the k minus 1. So at any rate, we have case 1 dealt with. Well, case 2 still needs to be dealt with. Case 2 has the second vertex being labeled k minus 1. Now again, it's a rigid motion of the particular n-gon, so this has to be k plus 1 because k is trapped between k minus 1 and k plus 1. And that would mean this is k plus 2, and this is k plus 3, and this is k minus 2, and so on. And what I want to notice is that inside, they are increasing in a counterclockwise motion, whereas outside, they are increasing in a clockwise motion. That's the dead giveaway that there must be some kind of a reflection going on. Well, the question is what reflection? So we need that we understand that there is a reflection going on. Now the question is can I write that reflection as a composition or a product of S and R to some particular power. I don't care what power it is. Well, let's put our thinking hat on. What I'm going to do is I'm going to realize that I know what r to the k looks like. Or rather, I know what r to the k minus 1 looks like. R to the k minus 1 in my outside cycle r to the k minus 1 has labels that look like k k plus 1, k plus 2, and k minus 1 over here, and k minus 2 over here. So I'm going to actually kind of highlight that, just those yellow labels. That was, of course, case 1. But now so this is what happens to the red ingon when we do r to the k minus 1. Well, now what I want to do is I want to reflect along that particular line of symmetry, which is the line of symmetry for the S1 flip. Because the S1 flip is the flip that goes through that top vertex. And it's just that we are looking at the yellow labels instead of the red labels here. Well, when we do that flip, we wind up getting these labels switching in pairs. And so now our labels look like k minus 1 over there, k plus 1 over here. This is going to be k plus 2, and this would be k minus 2 all the way around. And so what we find is that this case 2 picture is nothing more than r to the k minus 1 followed by s. So in other words, when we look at the case 2 picture, we're looking at r to the k minus 1 followed by s. And here again, when we start looking at things, there's another typo. That should read t is equal to s r to the k minus 1. And now what this means is that, every flip, to finish this up, let's see, to finish this up, okay, I want to look at, let's do one thing. To finish this up, I need to be thinking in terms of this very last thing. It says, hence, these two guys generate dn, and that we get this kind of a thing. Now I want you to keep that in mind. I'm going to explain that in the next slide for just a minute. What we now have is the n rotations inside Sn are just r squared, r cubed, r to the 4th, and so on up to r to the n, which is our do nothing, which the author writes as a capital 1. And this is where we have explicitly chosen r to be the permutation 1 goes to n minus 1 goes to n minus 2, all the way down to 3 goes to 2 and back to 1. And the n flips inside Sn, each one of them can be written as an r to the k minus 1 times an s. And this r to the k minus 1 is going to basically have something that goes to 1. So let's talk about every flip for just a minute. Every flip can be thought of as, if we take that ingon, and our original labeling looks like this. The new labeling is, well, somebody is going to land at 1. But because it is a flip instead of just rotation, the increasing direction on the outside has to go in the other direction on the inside. So this has to be a k minus 1 and this has to be a k plus 1 for setting up our way around the cycle. And we've already seen that that particular permutation can be written as do r to the k minus 1 times an s. And this is where our s is equal to the s1, which is 2 goes to n, 3 goes to n minus 1, and so on down to the last thing. And it's just important to remember that the last thing varies depending upon whether or not we are in an even in or an odd in. So I'm just going to write this as last thing. Well, to kind of wrap this up, what this means is that the elements in the set are r squared, r cubed, r to the fourth, all the way up to r to the n, which is going to be our do-nothing permutation, and then r followed by s, r squared followed by s, r cubed followed by s, all the way up to r to the n followed by s, which is just going to be s. There are 2 to the n distinct permutations in this set. And this set, let's just call this set S, this set S is known to be a subset of the dihedral group because they are all symmetries of the dihedral group. And the dihedral group has order 2n, and these two facts together say that that set is all of dn. Now, the very last thing that is in the statement of the theorem, so let's go back to that theorem for just a minute. I want to go back all the way back to the statement of the theorem. If we look at the statement of the theorem, this last thing here, the author leaves this for you to show, but I do want to kind of talk a little bit about why it's important, because you are going to be showing that on the next problem set. So what I want to do is I want to be thinking about why would that be so. So let's actually go all the way to the end. And so here, let's then look at why should SRS equal R inverse. That's for you to show. On the next problem set. But the implication is that if we look at any product, so if we are in dn and we have s and we have r, and we know obviously that s squared is equal to the identity and r to the n is equal to the identity. And we know this particular fact that you still have to show. The importance of these three things is that if I write something in the wrong direction, So just scroll up for a minute. Remember, all of our elements are written as first do the rotation, then do the flip. Well, if I wanted to say what element is first do the flip and then do r cubed, well, I can think of this in the following way. I can think of that as certainly being s r cubed s, because s is just e. So that doesn't change anything. Well, now what I can do is I can look at s r r r s. That's just breaking apart what r cubed is. And now I'm going to stick in a whole bunch of extra s's. S, R, SS, R, SS, R, and then that final S. This is simply a copy of E, and that's simply a copy of E. So I haven't done anything. But now I can reassociate. We have an S times an SRS times another SRS times another SRS. And if you think about that, what does that say? Well, that's going to be an S times an R inverse times another R inverse times another R inverse. And that would be S times R to the minus 3. Well, in Sn, R to the minus 3 is the same thing as R to the n minus 3. And so this would be S to the R in minus 3, which clearly belongs to our set S. And no matter what product you use, you can use these same three rules. So these three rules that I've just circled, let's circle them in red. These three rules can be used to rewrite any finite product of S's and R's in the form first do some rotation followed by a flip, or just do a rotation. And that will end this particular video.